Okay, we were discussing the moving average filter. So we have discussed in that the Han filter or the Hanning filter, which was yn is equal to 1 by 4 x of n plus 2 into x of n minus 1 plus x n minus 2. Okay. So when we have computed its frequency response, which was 1 by 2, 1 plus cos omega, and the phase response for this filter was minus of omega. Okay. And we have discussed that okay, for a sampling rate of 200 Hz, this filter provides attenuation of more than 20 dB beyond 80 Hz frequency. So it can be a low pass filter in that case. But if you choose a high sampling rate, this is not a adequate filter, okay, for filtering ECG signals. And in general, this moving average filter was like this. It was Bk x of n minus k from 0 to n. So at a particular instant of time n, this filter looks for the previous n or n plus 1 samples and multiply those samples with some fixed coefficients and add them together. And this window then moves or slides along the time axis. Okay. Now the frequency response of this filter and filter that can be improved if you have a higher length. You can say filter, or if you increase the length of this window. So we take a 8 length. Let us suppose you take a 8 length moving average filter. Okay. It means now in this case, what will be y of n? It will be 1 by 8 summation of x of n minus k, k from 0 to 7. Okay. So this filter at any particular instant of time will simply multiply at any particular time, suppose n naught, it will look into the previous samples in a window of 8. So previous 7, including this sample, it will see for the previous 7 samples and it will simply average them together. Okay. So multiply them with 1 and divide by 8. Okay. So average of these 8 samples. Then this window will move to the next position. So at next time n1, again it will see in a window of 8 samples and those samples are averaged together and so on. This is a moving average filter of 8 length. Okay. And if you see its frequency response, how it will be. So your yn is 1 by 8 summation of x n minus k, k from 0 to 7. So 8 length moving average filter. Or in terms of z transform, you can write it as h of z is equal to 1 by 8. It will be 1 plus z inverse plus z to the power minus 2, minus 3, minus 4, up to minus 7. Okay. And accordingly, you can find its frequency response h omega by replacing z with e raised to power j omega. So you'll get 1 by 8, 1 plus e raised to power minus j omega plus e raised to power minus j, 2 omega, 3 omega, 4, 5 omega, 6 and e raised to power minus j, 7 omega. Okay, or you can take it as 1 by 8 into 1 plus, you can take from this e raised to power minus j 4 omega as common. So this will become 1 and the rest of the terms they will be combined to generate again cosine terms. Okay. So we'll get 2 cos of omega plus 2 cos of 2 omega and plus 2 cos of 3 omega. This will be the magnitude response. Okay, and then you can plot it, and again I have phase response. In this case, the phase is not linear, of course. It is linear in piecewise manner. Now, see, one thing that we will focus here is if you find its frequency response, you can plot it. Okay, with respect to you can change omega from 0 to pi and plot its magnitude that you can get. But apart from that, this is now its transfer function h of z is basically polynomial in z inverse. Okay. And if you find the roots of this polynomial, you will get, of course, seven roots. Okay, the degree of the polynomial is 7. And in terms of the frequency response, or see what, let me discuss what is the relation between these location of zeros and this frequency variable omega in the z plane. This is the unit circle in the z plane, and on this unit circle we say okay that z transform converts to a Fourier transform. Okay, so h of z on the unit circle it converges to h of e raised to power j omega, or in fact z is basically a complex number r e raised to power j omega. Okay, so if you say okay r is 1, then your z becomes only raised to power j omega, which becomes a Fourier transform. So on this circle you have different frequencies basically. Okay, and how these frequencies are located. Now, since we have digital frequencies, you can have either from minus pi to pi, or you can take from 0 to 2 pi. This is the fundamental frequency range. Okay, so omega is equal to 0 means this point, or if in terms of z, this is basically z is equal to 1, because at this point omega is 0, so z is equal to e raised to power j omega. If omega is 0, the frequency is 0, it corresponds to z is equal to 1. Okay, similarly this point, it corresponds to omega is equal to pi by 2. So as this phasor or this vector rotates, your omega will go on changing. So it will start from omega is equal to 0, then omega will start increasing, it reaches to omega is equal to pi by 2, and then it further moves ahead, it reaches to the omega is equal to pi. So this point, it corresponds to omega is equal to pi. So at this point you have omega is equal to 0. So this point in z plane, it corresponds to omega is equal to pi. Okay, or in terms of z, it will be z is equal to minus 1, because omega is pi. So it is cos pi minus a sin pi. So cos pi is minus 1, sin pi is 0. Okay, similarly this point is j is equal to 1, j. Okay, z is equal to j, and this is z is equal to minus j. Okay, it means this circle, the frequency on this circle is basically 2 pi. So it starts from 0, as this phasor rotates, it goes to pi angular frequency. Then it again increases from pi, 3 pi by 2, and finally it comes to here. This again becomes 2 pi. Okay, 0 to 2 pi. Now if you write this in terms of the sampling frequency. Okay, so at any point on the circle, there is basically a digital frequency. It corresponds to a digital frequency basically. Okay, and in terms of omega, it is a frequency between 0 to 2 pi. Or another way to interpret this is that if you do not take from 0 to 2 pi, if you take from 0 to pi and 0 to minus pi, okay, if you take this frequency band, pi to minus pi, in that case, when this phasor rotates in this direction, anti-clockwise, it is a positive frequency, so it will span a frequency range from 0 to pi. And if the phasor rotates in this negative direction, it goes from 0 to minus pi. Okay, So upper half circle is now from 0 to pi. The lower half is from 0 to minus pi. So this can be interpreted like this also. Okay. So, so if you take this interpretation 0 to 2 pi, it means in terms of f and fs, now you have omega is equal to 2 pi f, or that is 2 pi into f by fs. So this corresponds to frequency of 0 Hz, this point, for any sampling rate. Okay, this is f is equal to 0. And then this frequency, when it reaches to pi, it means your fs or f should be equal to fs by 2. So this corresponds to a frequency of fs by 2. Okay, this corresponds to a frequency of fs by 4, and so on. Okay, so this either you can take it as minus fs by 4, or in terms of positive frequency you can take it as 3fs by 2, right? So this, now in terms of hertz, I am relating the frequencies now in terms of hertz. Okay, not in terms of omega. In terms of omega, it goes from 0 to pi, then pi to 2 pi, or it goes from 0 to pi or 0 to minus pi, whatever it is. But generally we have the frequency in hertz. So how you to locate that frequency in hertz on this unit circle, you simply divide it with the sampling frequency. Okay, so at any particular this frequency, which is omega, so in terms of hertz, it is basically 2 pi into f by fs. Okay, so if it means if at a particular frequency, if it is f here in hertz, so it should be less than of course fs. So if it is f, then if you multiply this, divide by fs and multiply with 2 pi, you will get omega. Okay, so this becomes, this frequency is at fs by 2, and then as you go ahead at this point, this is again fs. Here f is being equal to fs if it is 0 to 2 pi. Okay, this is how the zeros, their frequencies on this circle, they are located. Okay, and this is very important. See, when you design these notch filters that we'll discuss then, suppose you want to design a notch filter which is used to remove a single frequency of suppose 50 Hz. Okay, and let us suppose my sampling frequency is 500 Hz. So this is simply designed by placing its zeros on the unit circle in the Z plane. Because on the unit circle in the Z plane, it gives you a frequency response. Okay, and if there is a particular zero on the unit circle itself, it means that that particular frequency, the frequency response becomes 0. Okay, so if you have 50 Hz, if you want to design a frequency response like this, that okay, at 50 Hz frequency, the gain should be 0. It means in the unit circle, if I place a 0 on a unit circle at a point which corresponds to 50 Hz, so the frequency response at that frequency becomes 0. Okay, so this frequency is 50 Hz. So angular frequency, what should be my angular frequency? It is 2 pi into f by fs. So 50 by 50, 100. So I can take it as pi by 5. So if this frequency, if it is pi by 5, and if I place a 0 on this unit circle at this point, of course, since the zeros, the complex roots, they will occur in conjugate pairs. So I have to place a 0 here also. Okay, so if you design a filter like this, it will remove this 50 Hz component from the signal by placing two zeros. Okay, which are the complex conjugate of each other at a particular frequency of pi by 5. If it is pi by 5, pi by 5 is my frequency in omega radians. So what will be this point in the z? Since magnitude is 1, so z is nothing but cos omega plus j sin omega. This is one port Z1. Similarly, Z2 will be cos omega minus j sin omega. Okay, and omega is pi by 5. So from this you can get Z1 and Z2, the two roots. And so once you get the two roots, you can have a transfer function 1 minus Z inverse into Z1 into 1 minus Z inverse into Z2. So you will get a filter which is called as a notch filter. Isn't it? This is what is the meaning of the placement of zeros on the circle. Okay. Now what we are discussing here is we are saying that okay, I have a 8 length filter, so which will have a transfer function like this: z to the power minus k from 1 to 7, 1 by 8, and this will give you 7 zeros now. Okay, and if you compute those 7 zeros that I leave as an exercise for you, and if you locate these zeros in the z plane, now since my sampling frequency, if I take suppose 1000 hertz, so I will get 1 zero at a frequency of 125 hertz, another 0 at a frequency of 250 hertz, another 0 at a frequency of 375 hertz. This is 5 and 1 at 500 hertz. Okay. Now this and this, they must be in pairs, this must be in pairs, and these must be in pairs. So you have 7 roots. Okay. So basically you are getting this 125 actually hertz. From this you are basically calculating Z, Z1, Z2 up to Z7, 7 roots. Okay. Now this Z, if you find the magnitude of this Z1, that should be 1. It should lie on the unit circle, all these Z's. Okay. And then you see, okay, this Z1 will have the real part plus imaginary part. Okay. And once you get the real part and the imaginary parts, because this is a point in the Z plane, so this is the real part, this is the imaginary part. Okay, so R is 1, you can find omega simply by tan inverse of, so omega you can find tan inverse of imaginary part, real part. Now once you got this omega, you can locate this point on this circle at a particular angle. This omega you will get in radians. And then how you can relate this to hertz, because omega is 2 pi into f by fs. Now omega is known to you, and fs is the sampling rate that you have chosen as 1000 hertz. You can find this frequency. Okay, so this point in that case, a particular value of omega will correspond to a frequency of 125 hertz for Z1. Similarly for Z2 it is 250 hertz, 375 hertz, 500 hertz, and so on. So this frequency is minus 125 hertz. Okay. So this is minus 250 hertz, or you can take it as 750 hertz, like this. Okay. So this is again, you can take it as 750 plus 125 hertz, either this frequency or minus 125 hertz. Okay. It means when you plot the frequency response of this filter, the 7 and this 8 length moving average filter, since we have zeros at 125 Hz, 250 Hz, 375 Hz, and 500 Hz frequency rate. So if you plot from 0 to 500, 0 to fs by 2, you will have null points. Okay, so you will have a at 125 Hz, you will have a dip. Then at 250 hertz, then at 170, 375 hertz, and then at 500 hertz. The frequency response should be like this. Okay, because of the placement of these zeros on the circle, you will get zero gain at 125 hertz, 250 hertz, 375 hertz, and 500 hertz. Now see, of course, we are not interested in this band, in this frequency range, because for ECG signals, the maximum range is up to 100 hertz only. Okay, So these null points, they have no significance for ECG. Okay, and see, now between 0 to 125 hertz, since at 125 hertz its gain drops to 0, so it means for frequencies which are below this, it will have a high attenuation. So this will be a good filter in that case for ECG processing. Okay, so you can see its frequency response. This is the magnitude and the phase response of 8-point moving average vector. Okay, so at a frequency of, this is 125 hertz, then 250 hertz, then 375, 500, you have null points or dips because there are zeros in the Z plane at that particular frequencies. Okay, now from this you can see that okay, this is 100 hertz, or this is, so at 100 hertz your gain is almost around more than 10, minus 10. Attenuation is more than minus 20 dB. So you can have a sharp attenuation by increasing the length of this moving average filter. Okay.